because it will be tested. Electricity is a concept that you'll not miss to look at. All right, so going down to electricity, the first section you need to understand is how to define electromotive force and EMF. Electromotive force and the PD, which is the potential difference. So let's look at the first question here. State one similarity between EMF. State one similarity between EMF and PD. One of the similarities that has been given here is that both EMF and PD, they are measured in the units volts. But another similarity will be both represent the amount of work done per unit charge. So for EMF is the amount of work done to thing there. We can define EMF as the amount of work done to move a unit charge around a complete circuit. But if we are talking about potential difference, the PD is the amount of work done or energy transferred to move a unit charge between 2 points in a circuit. So you are going to give your definition as that. One difference between EMF and PD. What's the difference? Work done to move a unit charge around a complete circuit, that's EMF. But PDA, the PD, the potential difference, is the work done to move a unit charge between 2 points in a circuit. Battery consists 4 cells. If batteries are connected in series, the total EMF is going to be the EMF of one cell times the number of cells that you have there. So in this case, we're going to say it will be 1.2 times 4, and that is going to translate to 4.8 volts. The battery is connected in a circuit for 12 ohm resistors, which we are having here. And then we are told that the circuit diagram, we are supposed to calculate the total resistors. So something that we need really to appreciate here is that in this section, these resistors that we have here can be combined and create one resistor. And if we combine those two resistors, we are going to have a resistor of resistance 24 ohms. So which means this one of 24 and this one, they will be in what? They will be in parallel. So for total resistance in this parallel setup, we shall say it 1 over 24 plus 1 over 12 raised to power -1. So anytime you are going to work out total resistance when they are in parallel, what you're going to do is to add 1 over each of the resistance, then enclose the bracket, say raised to power 1, and that is going to give you the effective resistance when they are connected in parallel. And in this case here, we're going to have 8 ohms, but now this combined 8 ohms is in series with this other resistor that we have at this particular point. So which means that we are going to add plus 12 here, so that we have 8 plus 12, and that's the total effective resistance for this circuit is going to be 20 ohms. Calculate the reading on the voltmeter. If we are talking of the reading on the voltmeter, and the voltmeter we are talking about is this one here. Now what we are going to do first is to work out the total current in the circuit, and the total current in the circuit we're going to use the formula V over R, because the total resistance we have the total EMF of all the cells. Then we're going to say now total current in the circuit is going to be 4.8 divided by 20, and if we work it out, we're going to get 0.24 amperes. But we are working out now the voltage across the 12 ohm resistor here. So meaning is the total current times the resistance of this resistor, and that is going to give us 2.88 volts. Yeah. Then moving to the next question, question number 16. We are having here a potential divider. In this case, we're using two resistors X, which is a light dependent resistor, and then we have another fixed resistor Y, and we are supposed to connect a voltmeter to show how we can be able to take a reading of voltage across this resistor. So something that you need to remember is that voltmeters are usually connected parallel to any component because they are high resistance devices. The electromotive force EMF of the battery is 12 volts. In a brightly lit room, the resistance of the component X is 350 ohms. Now calculate the current in the circuit. So for us to work out the current first, we need to find the total resistance. So since we have been told this one is 350 and this 400, then we can be able to add them together because they're connected in series. The total resistance in this case is going to translate to what? Is going to translate to 750. Now, since we have also the voltage, the EMF that was applied as 12, we can be able to work out the total current in the circuits, and that is going to be 0.016. So that is the total current in this particular circuit that we have here. So in the event you are told to work out voltage in Y, you will take the total current times the resistance in this case here. And this is going to be the total current, which is 0.016 times 400. If you want this one, it will be 0.016 times the resistance here. For instance, if it was 350, you'll get the value there. So let's see the next question. Calculate the PD across component Y. And component Y, remember we were told this is having 400 ohms. So what does that mean? Is the total current times the resistance of that component, and that is going to translate to 6.4. In a dark room, the resistance of component X is very large, so we need to appreciate the fact that the resistance of a light dependent resistor increases when light decreases. So if you take this circuit in a dark room, the resistance of a light dependent resistor is going to increase massively. And then when that happens, if resistance of this component increases, it means there will be a larger potential drop in this particular section. Remember we said that in the event you want to calculate the voltage on this component, you will take the current times the resistance. So which means if there is high resistance in X when it's in a dark room, it means it's going to have a high resistance. So which means there will be a large voltage drop across X. So meaning the voltage drop across Y is going to do what? Decrease, because much of the voltage will be in X. So in the event you are given that question in an exam, what you are going to do and how you are going to respond is by saying when the resistance of X increases, more voltage drop across X, reducing the PD across Y, because the resistance of a light dependent resistor increases when light intensity decreases. Also, a thermistor is another type of variable resistor whose resistance depend on what? Temperature. When temperature increases, resistance decreases for a thermistor. Yeah, so you need to be very, very careful with that, so that anytime you are given a question, you'll remember that you learned it from Prof. Lang, and you will be able to score your marks. Now, we need to understand also the applications of these kind of devices. Application of a light dependence resistor, of course, it can be placed in circuits which are light sensitive, right? If you want to develop a circuit that can turn on at night and turn off a bulb during the day, we are going to use an LDR. So that you connect an LDR, you're going to connect your bulb across the LDR. For instance, we are going to, if you want to develop that kind of circuit, you are going to connect your bulb at this point. Let me just say here, we can connect a bulb at this point here, so that at night there will be high resistance, so there will be a lot of potential drop here. So this bulb is going to do what? Going to light. Right. Also, if we are talking about a thermistor is a high sensitive, temperature sensitive resistor. So, which means if you really want to make use of it, apply it in a given circuit, you can be able to put it in thermostats, whereby if temperature goes beyond a given limit, it can be able to switch off the current. Also, you can be able to use it in housing for alarms. If there is outbreak of fire, it can be able to trigger the circuit, and then an alarm is produced. So basically, that's what we can mention, but most of that is really done in AS physics, which we are going to do next year. All right, so the application, practical use of component X, already I've mentioned that. Now let us talk, change the gear and talk about electromagnetic induction. Remember, electricity can be generated using a magnet and a conductor. When a magnet cut through, rather, when magnetic fields cut through a coil, or when a coil cut through magnetic field, an electric current or an EMF is induced. This induced EMF result to the flow of current. So in this case here, we are having a spring, and this spring can make the material or this particular magnet oscillate up and down. And remember, the magnet is having magnetic fields. So as this magnet is moving up and down, it's going to make the fields cut through the coil. When the magnetic field cut through the coil, an EMF is induced in that particular coil through electromagnetic induction. So something else that you need to remember, if you want to increase the amount of EMF induced, you can increase the number of coils, you can increase the thickness of the coils, you can also increase the strength of the magnet, you can also increase the speed at which this magnet is oscillating within this particular coil. So those are the factors that you really need to consider when you are looking at this particular concept. Describe and explain what happens to the needle sensitive galvanometer. Now, you see, a galvanometer is a device that can be able to detect any small amount of current. It will deflect one direction when current flows in a particular direction. If current flows in a different direction, this galvanometer will deflect or move in a different direction or opposite direction, right? So what will happen to the center zero galvanometer? When this magnet move within the coil, the magnetic fields are going to cut across the coil, inducing an EMF. This EMF will result to a flow of current. Hence, the galvanometer is going to deflect. So how are you going to put it when they are going to ask that in your exam? You're going to say that the magnet moves up and down, as the magnetic field cut across the coil, it induces an EMF through electromagnetic induction. As the magnet moves down, the galvanometer deflects in one direction. As the magnet moves up, then again the galvanometer is going to deflect in the opposite direction, because current will be flowing in the opposite direction. Now, state the effect of using a stronger magnet. I've already mentioned here that if you use a stronger magnet, you are going to have stronger magnetic fields, which means that you are going to have a little bit more EMF induced. And in that case, if more EMF is induced, it means the galvanometer is going to deflect more. Are we together? It's going to show a greater deflection because a large current will be flowing. So I believe we are together up to that point. And if you're new to Proflan YouTube channel, consider subscribing so that when I'm going to upload the last bit of this particular series, you'll be notified. All right, another concept that is very, very, very possibly going, it's going to be tested, possibly is going to be tested. Another concept that is possibly going to be tested is the concept of transformers. What is a transformer? A transformer is an electrical device that can increase or reduce voltage. Let me repeat. A transformer is an electrical device that can increase or reduce voltage. The main parts of a transformer is a primary coil, a secondary coil, and we have a soft iron core. These two coils are wound together, but they are wound different arms of this soft iron core, but they are not connected. I'm going to show you how basically a transformer looks like, and then I'm going also to explain to you how a transformer works in a short while. Yeah, so let's look first. What are the kind of calculations that you need to know as far as transformer is concerned? Remember, there are two formulas that you are going to learn in this topic. Number one is the concept of power in is equals to power out. If the transformer is 100% efficient, it means that the power input should be equal to the power output. And that is going to give us the another formula, which is current in the primary coil times current voltage in the primary coil should be equals to current in the secondary coil times voltage in the secondary coil, because power is equal to IV. The second formula is V in the primary coil over voltage in the secondary coil is equals to number of turns in the primary coil over number of turns in the secondary coil. If you know these two formulas, you are good to go in this particular topic. So you are going to check what are you provided, what quantities are you given, and what are you finding. Now in this case, you can see we are finding the number of turns in the primary coil. So we are finding number of turns in the primary coil here. So we are going to substitute voltage in the primary coil is 25,000. Voltage in the secondary coil, it was given as 400,000. Then we are told number of turns in the primary coil is what we are looking for, and the number of turns in the secondary coil is 36,000. So if you substitute, you're going to get 2250 as the number of turns in the primary coil. And from here we can see this is, if I put that in my calculator, I'm getting my answer equivalent to 2250 turns in the primary coil. So that's why you can see in the secondary coil we have more turns. That's why it's a step-up transformer. So I'm going to take you through how a transformer works in a short while. Just let's look at this first. A washing machine has an electric motor and electric heater. The diagram we have here is a simplified form of that. State the meaning of electromotive force. So I believe this is the second time we are approaching this. Electromotive force, EMF, is the amount of work done or the amount of energy supplied to move a unit charge around a complete circuit. Then state the potential difference across the heater. If you look at the heater and the motor, basically those two components, they are connected parallel to the power supply. So meaning they're going to have the same voltage, which is going to be 230 volts. Calculate the current in the heater. So you're going to take the voltage in the heater divided by the resistance of that heater. Then we're going to get 9.2 amperes. Then we are told that the current in the motor is 1.6. So what you need to understand is that if we have a current at this point of 9.2 here, and there is another current here which is 1.6, when they join together and move through the ammeter, we're going to get a total sum of the two. So which means that we are going to add those guys together, and we're going to get 10.8 amperes as the total current in the circuit read by that particular ammeter. Now there is this concept whereby we can be able to determine the depth of the ocean using sound that is emitted from a boat. So in this case, a sound that has frequency, that is more than 20,000 kilohertz, it's called ultrasound or ultrasonic waves. And those that has less is called infrasonic or infrasound. So remember, the human hearing range is between 2000 to 20,000 hertz. So any sound that is out of that human hearing range is either ultrasound if it's more than 20,000, or infrasound, infrasonic sound if it's below 2,000. So at that particular point also, you need to remember the formula that can be used to determine the depth. Remember, this sound is going to travel to the seabed, then comes back. So meaning it's going to cover twice the distance. So for that reason, we are going to say now this is going to be what? This is going to be 2 times d over the time taken, that speed. But now with the information provided, we can say 1,500, because that's the speed of sound in water, is equal to 2 times 22 over time, so that we can be able to get our time being equivalent to 0.029 seconds. And then maybe you can be asked to describe and explain how the reflected sound wave received by the boat from the fish differs. The magnitude is going to be received will be weaker, since some of the sound wave will not be reflected back from the fish. Yeah, because actually it's small, so some of the sound waves will go down and they not be reflected. Now, moving further to electromagnetic induction, remember, if a current is flowing through the conductor, what will happen is that magnetic fields will be created around that conductor. Describe the magnetic field around the charging plate in terms of magnitude and in terms of direction. The magnetic field which will be created here will be constantly changing size and direction, because this is AC current, alternating current. So the magnitude of this magnetic field that will be created will be constantly changing size and direction. The strength of these fields will be very, very strong when it comes to when it's close to the coil, and they will be weak as you are moving a bit far from the coil. Also, we shall also talk about the direction of the magnetic field will be perpendicular to the flow of current of the coil. We are supposed to explain why there is a current in the secondary coil. Now we have a primary coil, and then we have a secondary coil. Remember, I promised you that I'm going to explain to you how a transformer works, but this is almost related to that. So let me just explain this first. When current flows through the primary coil, magnetic fields will be created around that particular primary coil. When these magnetic fields, which are constantly changing size and direction, are created, they will cut across the secondary coil, inducing an EMF through electromagnetic induction in the secondary coil. So something that you need to remember at this particular point is these two coils are not connected at all. They are not connected. But when a current flows through the secondary coil, it will create magnetic fields which are constantly changing direction, size and direction. So these created magnetic fields will cut through the secondary coil, and an EMF will be induced inside that particular coil. Now, that is it, and that is what we are supposed to state. And we are supposed to suggest why the transformer made from charging plates and a mobile phone is not 100% efficient. Remember, when current flows through a conductor, there is resistance. And due to resistance, the kinetic energy of the electrons will be converted to thermal energy. So which means that some of the electrical energy will be converted to thermal energy and will be lost to the surroundings. So that's why it's not 100% efficient. The mobile phone battery can be recharged using this charging plate, and it stores a total of 4.5 times 10 raised to power 4 joules. The voltage is 12 volts. Yes. So calculate the time taken to fully charge. Remember, electrical energy is given by IVT. IVT. I is current, V is voltage, and T is time, and time must be in seconds. If you are given in minutes during the exam, remember they are tricking you. They want to make you fail. Remember, time has to be in seconds. Don't forget that. So in that case, if we make T the subject of the formula, our beautiful formula will be time is equals to electric energy over current times voltage. And remember, current times voltage power. Yes. All right. And if you have not subscribed, I've realized some of my guys, my friends who watch my videos here, they have not subscribed. And I'm wondering why. Just support Profland so that this channel can grow. Yeah, just check. It's free. Just click on that subscribe button, like this video, leave a comment down below. I'll also appreciate as you are going to pass this exam by going through this concept that I'm mentioning here. So just subscribe. Right. So let me just take water waiting for you to subscribe. Right. 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 Thank you for subscribing. Let's move on. And working out this, we're going to get 59 seconds. And we are supposed to calculate the charge passing through the battery in 60 seconds. 60 seconds. We know that charge is what? Charge is given by current times time. And this means that our current was 0.63. Then the time is 60 seconds. So if we work it out, you're going to get 37.8 seconds. Oh my goodness, that's an international crisis, right? Charge is going to be in coulombs. Coulombs, the unit for charge is coulombs. Right, don't forget that. All right, so moving to question number 21. Still in electricity, you may be told to draw the symbol of a potential divider. A potential divider is drawn like that. If we are talking about a variable resistor, it's drawn like that. If we are talking about a thermistor, it's drawn like that. If we are talking about a filament lamp, is drawn like that with an X inside here. That's a filament lamp. If you are told a fuse is a device that has a thin wire within. So when more current passes, the thin wire is going to heat up, melt, and disconnect the current. This is the fuse. If we are talking about a diode, if they ask you about a diode, that is a diode. Yeah, if they ask you about light dependent resistor, we say this is it. If they ask you about a fixed resistor, you'll have to draw something like that. So basically, this is the basic type of symbols they can ask you. So let's look at this potential divider. And remember, the formula you use whenever you're given potential divider question is R out. R out is that point, the resistor you have where you are going to pick the voltage. So if this is R out, you are going to say V out is going to the voltage that will be tapped from this section, the voltage that will be taken out from that section is going to be R out over the total resistance, and the total resistance will be R out plus R. So meaning we're going to add this and this one, R out over R out plus R times the V in. The V in is this voltage that was supplied there. So which means that if you put that into perspective and then substitute, you are going to get your answer as 1.5 volts. Don't forget to write the units. Then the value of R is adjusted until the current is what? 1.7 milliamperes. So if you are converting milliamperes to amperes, you are going to multiply by 10 raised to power negative 3. If it's kilo, you multiply by 1000. Then moving on, remember in this section, you are going to use the formula charge is equals to IT, whereby we're going to get our final answer being equivalent to 0.51 seconds. Ross? Yeah, still we have a question that is servicing here for waves. I don't know how this guy got himself here, but it's fine. Remember the wave equation is V equals to frequency times wavelength. And if you're working out the wavelength, you have to say V over frequency. So the speed is 1500 divided by frequency, and the frequency has to be in hertz because we are given here kilohertz, so you have to take this 13 times 1000 so that you can be able to convert this in hertz, so that we can be able to get our answer equivalent to 0.12 meters. Furthermore, we are also going to look at the approximate speed of sound in air. Approximately, sound is 330 meters per second in air, but in water is approximately 1500 meters per second. So, and the speed of light, already we have mentioned that, is 3.0 times 10 to the power 8. So you need to remember that. The concept of magnetism. Under magnetism, you need to understand how to define magnetic materials and non-magnetic materials. Magnetic materials are those materials which are which are attracted by magnets, and non-magnetic materials are materials which are not attracted by magnets. You need also to understand the different examples of these magnetic and non-magnetic materials. You need to know how to define a hard magnetic material and a soft magnetic material. Hard magnetic materials are materials which are not easily magnetized, but once magnetized, they retain their magnetism for a long period of time, and they are used to create or produce permanent magnets. Then when we are talking about soft magnetic materials like soft iron core, are used to create electromagnets, because those are temporary magnets which can be created, which becomes magnetic when there's a flow of current, right? Yeah, so I think that is key. You need to understand the law of magnetism, that unlike poles attract, like poles repel. And further, we need to understand what do we mean by magnetic fields. How do we define a magnetic field? What are the characteristics of the magnetic fields? And if you are given a diagram, are you able to identify mistakes? Because we know one of the properties of magnetic field is that magnetic fields will never cross each other. So if you have a diagram whereby you see magnetic fields crossing each other, then that's wrong, that's a mistake. If you find a magnetic field pointing from the south to the north, that is a mistake. Fields point from the north to the south, right? And also fields are straight and straight and very close where the magnetism is strong. So let's talk about a student who is given 3 pieces of steel. 2 of these pieces are magnetized, 1 is unmagnetized. So we are supposed to describe and explain how the student can determine which is the unmagnetized using these pieces that I provided here. So something that we need to understand here, the student need to bring each of the pieces close to each other and observe the interaction. So if 2 pieces repel each other, then it means those are the magnetized. So it means that both are magnetized. So a magnet will attract both magnetized and unmagnetized steel. So the piece that will only attract but cannot repel, that is the unmagnetized. Now, going back to the concept of transformers, we need to understand there are 2 types of transformers. A step-up transformer, which increases voltage, and a step-down transformer, which reduces voltage. So if you look at a diagram, you can be able to determine whether it's a step-up or a step-down transformer. For instance, in this case here, we have a step-down transformer because we have the secondary coil has fewer turns than the primary coil. So meaning when alternating current, when AC current flows through this coil, it will create magnetic fields which are constantly changing size and direction. When those fields cut across the secondary coil, remember these 2 coils are not connected. So when those fields created cut across this secondary coil, an EMF is induced in this secondary coil through electromagnetic induction, then a current is going to flow inside here. Now let's look at this particular question. The main voltage supply, the voltage supply to the transformer is 240 volts. The output power is 45. But since we are told that this transformer is 100% efficient, it means power in is equals to the power out. So in the question, we are told calculate the input current. So if the output power is 45 watts, and then it means also the input power is 45 watts because it's 100% efficient. So that means we are going to use the formula power is equals to current times voltage. Since we are told the voltage was 240, then we can be able to find current as 0.1875 amperes. Then we're supposed to draw a label diagram of a step-down transformer. A step-down transformer reduces voltage. So the number of turns in the secondary coil will be less than the number of turns in the primary coil. You can see here, I've drawn it in such a way that we have more turns in the secondary coil, so in the primary coil, than the secondary coil. And then we have a soft iron core. So we have said the operation, how this transformer works is that when alternating current flows through the primary coil, it will create magnetic fields which are constantly changing size and direction. This created magnetic field will cut through the secondary coil, inducing an EMF in the secondary coil, thus a current flows. So basically that is all about electricity that I had to mention. So in the next tutorial, we're going to talk about we shall talk about radioactivity. We shall talk about stars, evolution of stars, and also we shall talk about space physics, so that we can be able to complete this entire discussion of physics paper 4 of Cambridge May June 2025. If you have not subscribed to Prof. Daniel YouTube channel, consider subscribing so that anytime I'm going to upload the next tutorial on this, you'll be notified. See you in the next video.